Okay, hello everyone. Welcome to this session of the COMSOC video seminar. Today is a Rump session. That means we will have 10 talks of 5 minutes each, so a more fast-paced version of our usual seminar. We have 10 exciting talks. How it will work is we will have 5 minutes. We will not have a Q&A after every talk for time reasons, but you are welcome to use the chat and put your questions there, and then you can interact with the speaker via the chat. After each half of 5 talks, we will go into a breakout session of 10 minutes. So today we will have 2 breakout sessions, and this time there will be no randomization, but instead you can choose which breakout room to join. You can change breakout rooms as well, and it is an opportunity for you to interact with the speakers in more detail. Okay, we will start with Alex Lam, who will talk about the exact price of cardinality for indivisible goods.
Okay, can everyone hear me?
Yes.
Okay, yeah, thanks, Dominic. So today I'll be presenting some joint work, which you may have seen at AAAI this year, but under a different presenter. And there are many different motivations for this work. I'll give one motivating example. Let's suppose you work for a charity that wants to fairly allocate M indivisible goods to N agents, and of course, utilities are additive and normalized standard. And you, as the educated scholar in fair division, you tell your boss all this stuff about EF1, round robin, prop one, all these fairness concepts and algorithms and whatever. But your boss just doesn't understand, doesn't care. He just says, oh, just give everyone K items each, or at most K items each. But in roughly 4 minutes, at least you'll be able to say, well, if you do that, then maybe we'll only achieve K on M minus N plus 1 of the optimal egalitarian welfare, or this expression times the optimal utilitarian welfare. And well, maybe your boss won't change his mind, but at least you both learned something new. Okay, so this talk mostly concerns the cardinality constraint. It's probably the most simple constraint there is. Each agent can receive at most K items. And the main question we're asking and seeking to address is how much welfare can we potentially lose when we impose a cardinality constraint? So we care about egalitarian welfare, which is the worst of agents utility. It's a fairness objective, and there's utilitarian welfare efficiency objective is the sum of the agents utilities. And we're seeking to quantify and compute the price of cardinality, which is essentially the worst case ratio between the optimal welfare and what I call the optimal cardinal welfare, which is the welfare from an allocation meeting the cardinality constraint. In other words, we're comparing the optimal cardinal allocation with the optimal allocation. So to start off, we'll give a very trivial and easy one. If you give me M, N, and K, I can tell you that the egalitarian price of cardinality is M minus N plus 1 on K. And the way we see this is, let's suppose we have one agent that values multiple items equally, but every other agent just values one item each. So as a result, the one agent that values lots and lots of items equally, they can only get K items, so they don't receive K on M minus N plus 1 utility, and our price of cardinality immediately follows. So this is somewhat straightforward, but the main result of our paper concerns the utilitarian price of cardinality, which is this somewhat weird non-trivial expression here. And interestingly enough, this is not directly dependent on N, but it's not independent of N either, because we impose that N is at least M on K so that we can always allocate all of the items. Now, this is actually a bit misleading because in order to achieve this expression, we need M and K to meet a divisibility constraint, which I'll show later. But if M and K don't meet this divisibility constraint, the utilitarian price of cardinality oscillates between these two expressions. Basically, we've narrowed the gap to at most 1, and there's a graph on the right here, which you can see the difference between these two expressions. So it's not that big. And the intuition behind this expression, or rather the construction of our worst case instance, is as follows. We let S be -1 plus the square root of 1 plus n minus 1 on K. And what we do is we let n minus S agents each have one utility for what we call a super item. So for example, the agents on the right here have one utility for this house. The remaining S agents, we'll let them have S on n minus 1 utility for each of n minus 1 on S items. And note that these agents value disjoint sets of items. Yeah, so essentially, if we compute the expressions, divide them, we exactly get this utilitarian price of cardinality expression. And note that the divisibility constraint comes from S and n minus 1 on S needing to be integer values in order to create this construction. If they're not integer values, then we basically round as much as possible and get as close as possible to this construction. We'll get a slightly lower price of cardinality. But essentially, we are able to prove that this is the worst case type of instance. Yeah, so that basically concludes the talk. As for other results, the full paper has some results for multiple categories. General N, we can do the egalitarian price. But for utilitarian price, we can only go up to 2 agents. Any more, we think that the expression is actually exponentially large. Like there's an exponential number of terms in the expression, which has a lot of max functions in it. So yeah, I think that concludes my time.
Thank you very much. The next talk is by Rakshita about best of both worlds, analyzing guarantees for equitability.
Hi everyone, I hope my screen is visible to you.
It's good. Maybe you can try full screen, Command L. No, sorry, didn't.
Doesn't seem to be working.
This works also.
Yeah. Okay, I think I just begin. So hi everyone. So I'll be talking about best of both worlds guarantees for equitable allocations, and this is joint work with Umang Bhaskar, Vishwa Prakash, and Aditi Sethi. So briefly going over the setup of the problem, we have n agents in m indivisible items and valuation functions associated with each agent, which are basically mappings from subsets of items to real values. And the goal of the fair division problem is to partition the m items among the n agents such that the allocation is fair. For the rest of the talk, we'll be considering all the items to be goods and all of our valuation functions to be additive and normalized. And yeah, so the popular fairness notions are mostly envy freeness and equitability. And this talk will mostly be about equitability. So an allocation A is said to be equitable if the self-valuation of every agent is greater than or equal to the self-valuation of every other agent. Now, from simple instances, we can see that an equitable allocation may not exist for every given instance. And so we move on to relaxations of equitability. One such relaxation is equitability up to one item or one good in this case. We call it EQ1. And for this, we need that if there exists an agent J whose self-valuation is greater than that of agent I, then there must exist a good in the bundle of J such that when the good is removed from the bundle of J, the equitability constraint for agent I is met. The best of both worlds problem is another way to work around the non-existence of a fair allocation. Here, what we're trying to do is we're trying to find a randomized allocation such that it's fair in expectation and in realization, it's almost fair. So this result from 2024 states that for additive valuations over goods, we can always find an allocation that is ex ante envy free and ex post EF1. So from that work, we propose a question of whether or not there exists an ex ante equitable and ex post EQ1 allocation for any given instance. So let's start with a simple case of two agents to develop some intuition. If we look at this problem geometrically, what we essentially want to do is we want to find two allocations A and A dash that are both EQ1, such that allocation A has agent 1 as its richest agent, and allocation A dash has agent 2 as its richest agent. And once we manage to find two such allocations, we can compute a convex combination such that we get a fractional allocation that is EQ. Now, we call an allocation A I biased if agent I is the richest agent in allocation A. And the first lemma that we present is that for two agents with normalized additive valuation, there exists a polytime algorithm that computes an I biased allocation, which means we can prove the existence of EQ plus EQ1 allocation for two agents with normalized additive valuation. Now, generalizing this result to the case of n agents, we can prove the theorem that an instance I admits an EQ plus EQ1 allocation if and only if for any hyperplane passing through the origin, we can find EQ1 allocations on both sides of the hyperplane. As we already saw, for two agents, such an allocation always exists. For greater than two agents, we've managed to find a counterexample. And in fact, this counterexample is with 3 agents and 4 items. For the special case of binary additive valuation functions, we managed to find an algorithm that is polytime and that computes an EQ plus EQ1 allocation with an additional property of obtaining the optimal social welfare also. Finally, the work also presents some hardness results. Specifically for a constant number of agents, we managed to show weak hardness. And we also managed to find a pseudo polynomial time algorithm for it. And for an arbitrary number of agents, we managed to show that the problem is strongly NP hard. I'd like to conclude the presentation with a few open questions that might be interesting to look at. Yeah.
Thank you very much. The next talk is by Jobst Heitzig about an upcoming project regarding aggregating safety preferences.
Hello, everyone. Can you hear me well?
I can, yes.
Super. Okay, so this talk's not reporting on any results. The only result I report on is that we got this grant, which is also a result. So this is I think, thrilling new project in the context of our Social Choice for AI Ethics and Safety initiative or attempt to form a research community around this question, where we have this workshop series. The next one is in 3 weeks in Detroit at AMAS. And this is the first project coming out of this, at least the first that I know of, that is freshly kind of funded by a UK funding agency that worries about AI safety. So we called it Aggregating Safety Preferences for AI Systems. And it's quite a large consortium. You see Niklas Böhmer, Markus Brill, who leads the project from Warwick, Paul Goldberg, who's in Oxford, Davide in Groningen, me, and Wes Holliday in Berkeley. And we're also advised by Vince Konitzer a little bit, so he's also kind of involved. So what's the context? ARIA has this vision of a form of AI that is different from what we know of current LLMs and what the big labs build in terms of agents. And they call it safeguarded AI. And the idea is that you have somewhere an AI system that is supposed to manage something, let's say the UK energy grid or something like that, a complex system and with safety issues. And it cannot just make decisions, but it can propose plans, propose actions, and so on. And some other agents, AIs, and so on, try to prove that these plans, that they comply with certain safety constraints. And they prove that within some model, of course, of the world. And that's called a world model. A lot of that whole project is about this world modeling and this automatic proof checking and so on. But there is a piece that calls for social choice. And that's the question, where do these safety constraints come from? Right? So for example, we could say someone wants the power grid to be down less than 100%, less than 1% of the time whenever the outside temperature is less than 5 degrees. That's a possible specification of what one could call a safety requirement. So this we call a conditional probability judgment. But safety requirements might also take different forms. It's not even completely clear what form they should take. Probably they should be specified in some form of language and should have something to do with probabilities like this one, but it's not completely clear how. And so our project starts with figuring out what is actually the right data type for it. What is the thing that should be aggregated, and what is the thing that it should be aggregated into? Should it be something like this, a set of such statements? Should it be maybe something like a set of acceptable probability distributions over some relevant state variables, like whether the grid is down or up and what the temperature is and all kinds of other variables? But you see, even though it's not completely clear yet, what is clear is that the set of alternatives has some structure and it's infinite, right? Because these probabilities could be anything. And that's, of course, challenging for the question of elicitation and for the question of aggregation. And then, of course, there's also bounded rationality. Whenever it comes to probability assessments, people are kind of notoriously bad in doing that. And then there might also be some ambiguity. So other forms of uncertainty that make this even more complicated. So we haven't done much work yet, except writing the proposal and getting the grant. And we will have 4 postdoc positions from fall, one in Warwick, one in Oxford, one in Groningen, and one in Potsdam. And will be 12-month short thing. And we'll advertise this when the call is out. But we're also welcoming all kinds of other collaborations, ideas. And so just get in touch with us. Thanks.
Thank you very much. The next talk is by Saar Cohen about online learning in coalition formation.
Hello, everyone. I'm Saar Cohen from Bar-Ilan University, and I'm going to talk to you about some new problem in coalition formation and online games, which deals with online learning of coalition structures which satisfy certain criteria. As a start, I'll start with some motivating example for our setting. Imagine that you have a set of computer science students who start their bachelor's degree together. And at first, they are not familiar with each other because they had no interaction in the past. So they want to know each other over the semester in order to decide how to form, for example, study groups in order to enhance their learning experience, their successes, etc. As part of this, the preferences of those students/agents may even change over time depending on the coalitions they join to. And the question here is what kind of partition coalition structure we would like to achieve. We could ask one goal is to find the best partition. I'll talk later what is the best partition that we consider. Another possibility is to consider scenarios where agents have some kind of self-interest and they follow all their selfish needs and try to selfishly maximize their own utility. So if we take the example we have here on the left, at day 1 of the semester, all the students come to the campus. They don't know each other, so they would partition themselves into some study groups. But the next day, they have more knowledge about the people they joined to their study groups, and so on. And then they make more better decisions over time based on what they learned in the past. So all these example and other situations fall under online coalition formation, where agents repeatedly form coalitions in order to attain common goals. In this case, they want to study together for some exam or some project. So our main contribution on that part is proposing new models for studying online learning in coalition formation. we have several results regarding that problem, and in all of them we devised optimal online algorithms, aka learners that maintain a partition over time while interacting with the environment, which may be either other agents or you can model the environment as some kind of an adversary that wants to push the algorithm to some worst case performance. So the first goal, which we talked about earlier, is finding the best partition, which essentially means that we would like maybe to maximize the cumulative social welfare over time. So results on that part we published at ICHKA last year, and essentially this can be achieved by optimizing certain notions of regrets. We considered several notions. If anyone wants to hear about a specific one, you can ask me later or in the chat. And as I mentioned earlier, the main contributions here are algorithms with optimal regret bounds. For our second objective, we consider scenarios where agents act selfishly. Namely, each one wants to selfishly maximize their own utility. And we focused on cases where single agents' desires / incentives motivate them to not want to deviate between coalitions. And thus, we focused on approximate Nash stability, which essentially means that no one wants to improve their utility by moving between coalitions on their own. We considered online algorithms for two different scenarios. The first one we published at AAAI this year about collective data utilization. Can view it like a centralized setting where agents share information through some common data platform which they use in order to learn over time their preferences towards other agents and then make better decisions. The second setting is a decentralized setting, which will appear at ICHKA this year, which essentially means that each agent only makes decision based on local information about coalitions at each round, without sharing information with others. So in order to achieve this kind of goal of obtaining some approximately Nash stable outcome, the goal of the algorithm is to minimize Nash regret, which essentially measures how far the solution is from being approximately Nash stable at each round. So minimizing Nash regret will eventually yield some kind of approximate Nash stable outcome. For both centralized and decentralized settings, we provided Nash regret bounds that are optimal in their dependence on the number of rounds, and polynomial in the number of agents, which is crucial here because the space of joint strategies is exponential in the number of agents, and existing algorithms for similar settings said they depend on exponentially on that kind of parameter. So this solves a really big problem. Also in other settings as well. So as ongoing and future work, we would like to consider other classes of Hedonic games, other adversaries, other solution concepts, and develop online algorithms which also deal with cases of partial and noisy feedback, have no regret guarantees for each agent which adopts them individually, and many more. So if you have more questions, you can contact us. Thank you.
Thank you very much. The next talk is by Vishwa Prakash about recent progress on EFX allocations. Looks good.
Hello, everyone. Can you see my screen?
Yes.
Okay. Hello, everyone. I'm Vishwa. I'm a PhD student at CMI. So I'll be presenting some of the recent progress we had on EFX allocations. I'll be presenting some results from different projects with collaboration with Pratik Ghoshal, Ruta Mehta, Prajakta Nimborkar, and Nitin Verma. So we consider a fair division instance with n agents and m indivisible goods. Each agent has value for each good. This is given as a matrix of non-negative reals. In general, evaluation is defined for any subset of goods, but we consider only additive class of valuation, where value of a set of goods is simply sum of value of every single good in that set. So this is the general fair division instance. So an allocation is a partition, and we can partition such that a bundle xi is given to agent AI. And we might, this is a complete allocation. There can also be partial allocation where all the items are not allocated. So our interest is in the notion of NV-free allocation. An allocation is said to be NV-free if for all agents I and j, Vi of xi is more than or equal to Vi of xj. That is, from agent i's perspective, she should believe that she got a better bundle compared to every other bundle. So, but we can quickly see that NV-free allocation need not always exist. Consider two agents with one valuable good. Whoever you give it to, the other agent is going to be envious. So Karayanis et al. Proposed a nice relaxation of NV-freeness. It's called as the NV-free up to removal of any good. So an allocation is said to be EFX if for all agents I and agent j, Vi of xi is greater than or equal to Vi of xj minus any good h in the bundle j. That is, if you consider two agents, agent A might envy agent B, but removal of any good, in fact, the smallest good according to agent A, which might be a bag, and the envy should go away. So this is called as a EFX allocation. And we can quickly also see that both of these can be relaxed further by a multiplicative factor. An allocation is said to be alpha EFX if Vi of xi is more than or equal to alpha times Vi of xj. And similarly, Vi of xi is more than or equal to alpha times Vi of xj minus h. And so since we are dealing only with goods, it makes sense for alpha to be between 0 and 1. So coming to the existence of EFX allocation, the big question is, does every instance admit a complete EFX allocation? And this question is open and is quite popular and for the last 5 to 10 years. And many people consider it one of the biggest problems in fair division. So what is, until now, what is known about one EFX is, we know that it exists for two agents. You can always find an EFX allocation. This is due to plot of garden. And also EFX exists for identical agents. That is, when all the agents have identical valuation function, then we can always find a complete EFX allocation. So then Mahara later showed that EFX exists for two types of agents. That is, if you can partition the set of agents into two groups A and B such that everyone in the same group have identical valuation, you can always find a EFX allocation. Then Chaudhary et al. Showed that EFX actually exists for three agents. This is EC 2020 and also in JACM work. And here what we show is we can further generalize this to show that EFX exists for three types of agents. That is, if we can partition the set of agents into three groups such that everybody in the particular group have identical valuation, then EFX, we can always find an EFX allocation. This generalizes both Mahara's result and Chaudhary et al.'s result. So coming to alpha EFX, so what was known is a 0.5 EFX always exists due to plot of garden. And then later, Amanatidis et al. Further give a better bound, so showing 0.618 EFX always exists. And then more recently, Amanatidis et al. Showed that if for instances with at most 7 agents, you can do better than 0.618, and you can in fact give 2/3 EFX allocation. So in this work, what we show is when there are 4 types of agents, previously we considered 3 types and we give EFX, but when there are 4 types of agents, we can also in fact give 2/3 EFX, which is better than the 0.618 EFX allocation. And coming to another notion of relaxation is EFX with charity. So consider any partial allocation on a set of goods, I mean, G minus C, where C is the set of unallocated goods and you have an allocation on G minus C. So this allocation is said to be envy free up to any good with some charity. If X is EFX allocation of the items in G minus C, and nobody envies the set of unallocated goods, which is C, that is for all agents I, VI of Xi is better than VI of C. So that is to say no one envies the charity. So the goal here is to give as little charity as possible so that it is closer to a complete allocation. So what is known here is Chaudhary et al. Showed that we can always find EFX allocation with at most n minus 1, where n is the number of agents, n minus 1 goods given to charity. Then later, Berger et al. Gave a better bound showing that EFX exists with actually n minus 2 goods, at most n minus 2 goods given to charity. In fact, they showed that when n is 4, that is just for 4 agents, you can do better than n minus 2, and you can in fact give EFX allocation with at most 1 item to charity. And in a different, in a slightly different flavor result, Akrame et al. Showed that you can actually do a trade-off of approximation factor and charity. You can achieve sublinear charity, that is in terms of n, if you are willing to compromise on some approximation factor. For example, if you plug in epsilon as half here, you can get half EFX with order root n charity, which beats both this, but it compromises on approximate factor. So what we show is when there are k types of agents, that is, the given set of agents can be partitioned into k groups with identical valuation, you can actually achieve k minus 2 charity. Here the charity is a function of number of unique valuations rather than number of agents itself. And we also showed that when there are k types of agents, you can again get sublinear charity in terms of not the number of agents, but number of unique valuations. So this is some recent progress on EFX allocation. So I will take questions in the breakout session. Thank you.
Thank you very much. Before we go to the breakout session, a few announcements. Ola Endres has an announcement.
Yes, thank you very much for giving me a few seconds to say something about our new project. I'm going to put a link in the chat. Maybe you've seen already Umberto Gandhi and I have been in recent days advertising postdoc positions, and there will be many, many more postdoc and PhD positions. So if you are looking for such a position, or if you have a student who might be looking, in particular next year, I think probably most positions will come out next year. There are interesting opportunities. So it's a project about digital democracy. How do you build an online platform where people can deliberate over political questions in a meaningful way, and how can we collect their preferences and so on. Of the 4 people leading the project, 2 people are doing computational social choice. So this will be a large part of the project, but there's also a political scientist and somebody who's doing complexity science and collective intelligence and things like this. So if people are interested, please have a look at the website. Thanks.
Thank you. And let me all remind you that the COMSOC conference or workshop rather is happening this September in Vienna, and the submission deadline is coming up on the 8th of May. Probably many of you will want to submit to that workshop, which is the workshop where this community gets together, and it's also a great opportunity to get very good reviewer feedback in my experience. Okay, great. So we'll now go into breakout rooms. These breakout rooms are labeled with the names of the speakers. I recommend that the speakers actually go to the room with their label on it, but that's not technically compulsory. And then we'll see each other in 10 minutes from now. Okay, welcome back, everyone. For this second half of the Rump session. Our next talk is by Piotr Faliszewski, who's going to talk to us about the guide to numerical experiments on elections in computational social choice.
You. Yeah, so maybe some of you actually know this paper already. It was a survey paper, HK24. And essentially what it is it's a kind of a city guide, but also a how-to guide on how to essentially run experiments or how experiments were run in COMSOC literature. The idea is that we just collected COMSOC papers about elections and experiments and see what we can, what conclusions we can derive from that. So collection of the data was, we're looking at AAA, AMAS, ICHKAI. And the HK24 paper actually had data up to 23, and we're committed to actually updating this survey. So currently, privately, I have data up to 24, and this will become public in hopefully not such a long time. By keywords, we just realize which papers are about experiments and then do some manual checks. So for example, out of the HK23 papers, there's like, I mean, there's thousands of them. We are actually, well, 846, we shortlist 41 and then do manual check and retain like 7 with actual experiments. Basic statistic is that so far we have nearly 180 papers with experiments in these conferences. Some ordinal, some approval, some papers actually have both. There are nearly 300 authors. Here you can see a list of the most experimental authors with up to 2 papers. Somehow we can see why I was interested in the topic. Here are also some other interesting statistics. And one thing to actually that gets me at least a bit worried about what's going on in our field, which is, well, we see that we still have this kind of nearly exponential growth of numbers of papers in AI conferences, and AAA responsible for a big chunk of it. And AAA grows, and while AMAS and ICHKAI actually kind of stay nearly fixed. But COMSOC papers with experiments on elections actually stay relatively, maybe kind of constant. We had a kind of large increase in 23, but this seems to be covering for the pandemics, which is actually the news from the 2024 analysis. We see that more and more papers are about approvals. So in actual numbers, it's a bit of a decrease now, but proportionally, it's actually increasing. Now, some conclusions we can get from analyzing these elections is, for example, the sizes of data that we're looking at. So, for example, this is a heat map of sizes of elections people considered. So, for example, there are small committees. There are institutions which have relatively few candidates, but more voters, or politics, which we almost apparently never study in our papers. We have few candidates, but thousands of voters. There's the ground truth setting where we have potentially lots of candidates, but not so many voters. Participatory budgeting data, which again in our synthetic data is not so present, but it is in Publib, and that's what a lot of these papers do. And then there's this small dip that kind of apparently only I study, or actually that's not even true. It's the multi-winner lab with about 100 candidates, 100 voters, which seems to be a nice setting for that. So if we look at Publib, indeed, it has the it's mostly of the data in the PB area. Preflip has both small institutions, politics, and ground truth. So these actually are covered in reality. So that's nice. And I won't go into what cultures we're using. These are in the papers. Experiments are not yet compulsory, but they become, at least I would say, if you cannot make an experiment on your paper, then maybe, well, it means you're very theoretical, and but maybe it would be nice to think of a way to do it. And there are 2 things I want to also say. My project that is finishing in about a year called Pragma will have to have a workshop. We promised to have a workshop, and we're planning to do it somehow this year, hopefully after AMA's deadline, probably mostly geared toward PhD students and early stage researchers. So keep a lookout for that. And part of the project is, I mean, there's the ICHKAI paper. There's also an archived version of that paper, which has more data. But most importantly, there's also a website that actually has our database. And one really nice use case that we had recently was a reviewer said that our paper on approvals is using completely nonsense notation because he would prefer something else. So we went to this database. I put filter, I put approval. And this gives me a list of all the papers with experiments on approval elections, and there's not that many that happened over recent years. We looked at them, and you can see almost all of them used notation as we did. So we could actually respond to this request. Actually, look at this paper, look at this database, look at papers, these numbers. They all do what we do. And it would be nearly impossible to do it without the guide. So, well, that was nice. And I hope this tool will be useful for you. And thank you very much.
Thank you very much. The next talk is by Ben Cookson about constrained, fair, and efficient allocations.
Hello, everyone. I'm Ben. This is based on a paper we presented at AAAI this year, myself and Soroush and Nisa, who are both here today. So what we're primarily concerned with is these fair division problems that are subject to some complex constraints. So one practical example of this is allocating shifts to nurses, where you have these constraints, along with wanting to make sure that the allocation is fair and efficient with respect to these nurses' preferences. You have these additional constraints, like no nurse can work more than one shift at the same time, or 2 shifts a day, or 5 shifts a week, things like that. And how this setting is typically modeled is that, along with the typical fair division setting with M indivisible goods and agents' additive preferences, we also have this collection of valid bundles. So we have this predefined collection of valid bundles that agents can receive, and we want to make sure that any allocation we return, each agent gets one of these valid bundles. And particularly, a very common way to sort of model these valid bundles is to say that they're matroids, which capture a lot of natural cases, such as the shift allocation problem. So technically, when we say this, what we say is that the valid bundles have to meet these 3 matroid axioms, meaning that the non-empty set is valid, or the empty set is a valid bundle. It's hereditary. So if some set of items is valid, then every subset of that set of items is also valid. And they have the exchange axiom. So if you have 2 sets of valid goods and one is bigger than the other, then you should be able to take a good from the bigger set and move it into the smaller set and have that still remain a valid bundle of goods. And with these axioms in place, it's an open question that if your valid bundles form a matroid, can we guarantee that a fair and efficient allocation always exists, meaning that allocation that meets NV freeness up to 1 good and is Pareto optimal? So what we show in our paper is our first result is that given a matroid constrained fair division problem, where then the allocation that maximizes Nash welfare, so the valid allocation that maximizes the utility, the product of agents' utilities, will get a half approximation of EF1, and it will also be Pareto optimal. So this is a very nice, clean result, but one downside of it is that because of an interesting quirk of how constrained fair division works, that is too complicated to explain now, but if you want to talk to me in the breakout session about it, it's pretty interesting. But enforcing Pareto optimality may require us to have to return an incomplete allocation. So the most efficient thing to do may be to leave some goods unallocated, which is fine for some cases, but you could think of in problems like the nurse shift allocation problem, then we can't just not allocate a shift in the name of efficiency. In that case, making sure every shift is given to some nurse is much more important than being Pareto optimal. So we introduced this second theorem, which states that if your constraints, your valid bundles, form a base orderable matroid, which is a special class of matroid that generalizes these nurse shift allocation problems, then the allocation with maximum Nash welfare among all those complete allocations will achieve a half approximation of EF1 and will be Pareto optimal with respect to all complete allocations. So it may not Pareto dominate some of the incomplete allocations, but among the complete allocations, it will be efficient. So we proved some other things as well, but those are the 2 most interesting and cleanest results. as far as open questions in this space, there's a lot. There's the big question of general matrix constraints. Do EF1 and PO allocations always exist? But I think the most probably interesting and most approachable problem is this simple case of laminar matroids, which captures the shift allocation problem. So in these constraints, you're given a laminar set of the goods, a laminar set family of the goods, which means basically like non-technically, it's a hierarchy of the goods as like you see below. So you have like days, and then those are assumed by weeks and things like that. And you have these upper bounds. So each agent can only receive a certain amount of goods from each set. And under constraints like this, we don't even know if a complete EF1 allocation always exists in this setting. So that's what the next step we've been trying to look at in solving these constraints allocation problems. And I think that's probably the most approachable problem. Yeah, that's it.
Thank you very much. The next talk is by Nick Mattei about deep voting, learning impossible voting rules.
I love this title, but Ben Abramovich never wants me to use it. So I signed up for the talk, so I get to use it. So this is joint work with Leo, who's a student working with me, Ben, who is a postdoc, and Avinash, who is a former coworker at IBM. So we've submitted this paper once or twice. We keep getting we're landing in this weird space between social choice people who maybe don't understand all the terminology of machine learning and machine learning people who think everything we do is trivial. So it's been a very interesting road toward this idea of, all right, well, let's use machine learning to learn things that we're not supposed to be able to learn. That was my whole plan. It's my pitch that I want to do. Why do we want to do this? Well, when we do preference aggregation, right? A lot of the work that we've seen today is like, okay, well, let's restrict the preference space. Let's do some kind of restriction because we want these solution concepts. We want these things that we can't actually get. And so why not try to learn them? I mean, that's the joy of having a neural net, right? This is a universal function approximator. Just because I can't think up a scoring rule that gets me what I want, maybe the machine is smarter than me. That's that basic idea. So, but there's a bunch of problems with trying to use neural nets. It turns out you just don't like throw a bunch of data into a trash can and something comes out, even though that's how it seems to be used in practice a lot of these days. And there's a lot of terminology where I feel like there's a lot of confusion and what things go on. So first things first, what do? Well, we characterize what in the machine learning literature we would call embeddings. And here you and I and us in this friendly COMSOC community would call profile representations, transforms. I'm not really sure what you would want to call it. There's a lot of different words depending on the literature. I'm sure we can get that out of Piotr's database. But the idea, right, because in any neural net, you need a fixed size vector, unless you're going to do it recurrent or you're going to do it sequential, which is not a good idea for voting rules for reasons that we can get into for other things. So one of the first questions that we kind of go through is like, okay, well, explicitly listing out the profile is terrible because this is not fixed, right? It doesn't have a fixed size. It's just a whole bunch of votes. And so what do? Well, let's look at these embeddings. And if you go in the machine learning literature, there's other people doing this and they're doing a terrible job of it because they're making up things that make no sense. And they're trying to embed this stuff, not using something that we all know, like the rank frequency matrix, or I don't know, the tournament matrix, like things that we use all the time. And in reality, these are just embeddings, right? These are fixed size vectorizable representations of profiles. So let's use those. Questions come in, how do we use those? Are there things we can't learn because of this, which is a nice learnability type questions. And so what do? Well, the first thing we do is we blow past this paper from NeurIPS where they made up some embeddings that made no sense using just a basic neural net. So that's sort of the first experimental result. And then the last thing we do, which I'll talk about quickly because I'm going to try to stick to my 5-minute time, is can we use this to learn what I would call an impossible voting rule? So let's talk about this quickly. All right. Again, this fixed size embedding is a big thing. So half of our paper is just theory over which kinds of transforms are preservable under the various embeddings that we have. Another thing that is kind of goofy, and if you look at a lot of machine learning voting papers, one thing that happens is, in reality, neural nets give you a distribution, right? And these look more like probabilistic social choice functions than they do single winner rules. And a lot of the error, a lot of the kind of the problems in some of the experiments, at least in my opinion, that comes out of this is instead of looking at this output layer, which would be, we then run through some kind of softmax or sampling, we're just looking at whether or not the winner is the right one. And why would you do this? This makes no sense. It's harder to learn. It's a harder function. It's not as continuous. So it's not as nice. And so we formalize all of this as a problem of learning a probabilistic social choice function using things like stochastic dominance and stuff like that in our loss functions. So this is non-trivial to do so that you actually get learnability. But it seems so obvious, right? Like, let's look at the distribution of our candidates instead of looking at what the actual output is. Turns out some people get a little confused by that, but that's in the nature of how a neural net works. All right, so what is the first thing we do? Well, we have a big table. We prove that, there are some rules that you could learn or maybe could not learn under the various transforms, right? And this has to do with the way that, if you think back to these profiles, if I move a vote, right? If a vote changes from one to another, there's going to be certain axioms and certain rules that are not going to be preserved by that movement from the full profile. So we go through, okay, fine, we got a hole, big deal. That's, question mark table papers are a hallmark of social choice over the years. And then we take that and then we say, okay, well, can we learn it, right? So then we slam a dump truck full of data, as they all know, I like to call it burning up dinosaurs on our supercomputer. And we end up learning very well. And it turns out, as you would expect, because this is a group of smart people, depending on the embedding that you choose, your ability to learn and the speed that you learn varies, right? And then we end up with some stuff. This is L1 losses. So L1 is just the distance between the probabilistic social choice vectors. These, everyone's sort of like, well, are these good or bad? I mean, the way that you read this is using rank frequency. Under plurality, we have 0.0007 bits of probability distribution in the wrong spot, right? So I would argue that's pretty damn good. Sorry. We can do this in sample. So this is with 7 voters, when 7 candidates and 29 voters. We can do this out of sample. We can scale up the number of voters. We lose very little in terms of accuracy here. We can run this for single winner, which is what a bunch of the other papers do, which doesn't make any sense. Turns out that we do better than all of them. With this, we get a lot of preservation in terms of being able to completely recapture rules as you would expect. One of the things that I think is the coolest, and we're still pushing ahead with, and I think we need a bit more results on, is so once you have a neural net, right? Once you have the parameters of this model, you can take those and then you can fine tune it on another loss function. So this is called transfer learning, fine tuning, pick your word, that's what we do. So what do we do here? Well, we take the nets that are trained on rules, right? Because the first thing we want to figure out is, can we learn a rule? And then the next thing we want to figure out is, can we modify that rule in a way that preserves our accuracy on the rule, but also gives us something else? So here we look at participation, right? Which you can argue is a type of attack on a voting rule. So this is whether or not you can successfully abstain. And it turns out that if you then do a fine tuning step with this, you can actually do better at being robust to participation. You don't get it perfectly, obviously. And you can maintain your accuracy over a number of rules that are not participation proof from the literature. So I like to call these impossible voting rules. Ben Abramowitz doesn't like it when I say that, because there's not actually an impossibility for some of these, especially under probabilistic social choice functions. But I submit that these are rules that are better at retaining a particular rule outcome and better at being resistant to participation. There's all kinds of fun stuff in here. I'm happy to talk about it. How do we do other axioms? How do we mix these things together, et cetera, et cetera. And since everybody else is advertising, I'm advertising. I got a postdoc. Come hang out in New Orleans and do fun stuff. That's me.
Thank you very much. The next talk is by Josh Young about bridging voting and deliberation with the method of Equal-Shares, field experience in Switzerland. If Josh is here, hello. Oh, there.
Hello, can anyone hear me? Hello?
Yeah, I can hear you.
Yes. Yes, sorry about that. Sorry, it's gonna yeah, so the presentation is gonna be a little bit informal, as I'm currently on the road and currently traveling. And so this is kind of a very brief summary of what I've been doing. And yeah, so am I sharing my screen correctly?
You probably can click on slideshow at the top. Then yeah.
Yep. Yeah, so
Right.
I want to talk. So like I said, I've been on holiday traveling, and I apologize for the unprepared presentation, but I really want to talk about how the voting space can be bridged with deliberation. And I've been looking into how to apply voting aggregation rules and voting rules, and also social choice theories in application in real life. And what I realized through my participation in different programs, for example, in the Start Idea, in ADO, the first participatory budgeting program, and also Kutu Committee in Winterthur, is that there's always the city, they use participatory budgeting as a tool, as a mean to sort of engage citizens, to bring them into participation. And the citizen actually have a lot to voice. They actually want to come into discussion. They want to be able to contribute to deliberation and actually have some input. And so there's a space in between deliberation and voting that's underexplored, in my opinion. And I wanted to be able to answer how deliberation can guide voting, and how voting can guide deliberation. Just for context, we've been doing lab experiments with a lot of great authors, also some of them in present here, to sort of explore how voting system can be designed to sort of be more, for example, to achieve fairness, but also to achieve legitimacy, and how people interact with the system and the usability of it. And I wouldn't go into this time due to the time limit, but some of the quick summary from the lab experiment is that there's, yeah, sorry, I wouldn't go into detail for the lab experiment outcome, but we used lab experiment insights for the Start Idea ADO participatory budgeting. We use cumulative voting for input, and also method of equal shares for the aggregation. And what we found is that instead of all the projects congregated in the inner city, the projects were actually evenly allocated across all the different districts, and it's a much more decentralized and much more fairly proportional distributed outcome. But I want to focus on deliberation and voting, and there's always, for deliberation, there's the benefit, the pro is that there's the deep reasoning and people coming together. And I want to mention that when participatory budgeting first started, Dominic actually reminded me of this, that when it first started, that participatory budgeting was about people coming together to deliberate. And while social choice these days have really focused on how to aggregate a vote, it really lack of that combination of bringing people together and having that informed discussion where people can actually make educated decisions. So what we attempted in the field in Kutu Committee Winterthur is that we allocated part of the budget for voting and allocated part of the budget for deliberation. And this is two iterations I want to mention. The first iteration happened last year, and the context is that we have a Kutu committee, and every year 40 randomly invited citizens. It's an interesting idea of participatory budgeting and citizen assembly, people coming together to deliberate and make informed decision. And so I coined it as budgeting assembly. That's really trying to combine the benefit of both participatory budgeting and citizen assembly. I've also seen papers that's coined this as a new style participatory budgeting that really combine the virtue of both of the democratic innovation. So here's some of the impression. These are the pictures I took. People would go around the room and learn about the 120 projects, and then they would be formed into groups and come into discussion. And at the end, what I implemented was the algorithm that's a variation of method of equal shares. I'll go into a little bit more details later. So at the end, people have this platform to interact with and also play with, to sort of see how the outcome can be changed if the design had been different. And another detail I want to mention is for the iteration last year, we also attempted combine this idea of enclave deliberation. That means for marginalized group and people with niche interests, they feel more comfortable, or they will be able to confirm their preference if they are grouped with people with similar preferences in the first round, and then go into diverse deliberation in the second round. So this is what we attempted last year. So what we did was there was an online voting phase where people voted online, and then using the online votes, we were able to sort of do clustering in order to inform deliberation, to group people into different groups. If they have similar preference, they're put into similar groups. And traditionally, this was more commonly done by demographic, like the enclave deliberation, like maybe based on race or gender, age. But in this case, we use online vote for direct preference. So there's no demographic stereotypes involved, and use dimensional reduction to sort of group people into different groups for the discussion. And the reason we use two-dimensional is for equal size grouping, and also for people to easy understand what happened in the background and see who they are grouped into the similar group. And what we figured out is that, for example, there's two different settings. One is people in homogeneous interests, and one round is with people in heterogeneous interests. And in the homogeneous interests, we found that younger and female participants were able to secure their interest better, and we match it with their online vote beforehand and the outcome that was sort of finalized in the aggregated outcome. And we found that so older male participant, they potentially have more of a say in heterogeneous group. But that could be due to multiple reasons. One could be younger female participants are more open to different ideas. It could also be some people tend to be more dominant in a heterogeneous discussion. So this is a power structure we haven't looked into. But then in the second iteration, what happened this year, we use a different algorithm that combined the idea of priceability into the calculation. So like I mentioned, 50% of the budget is distributed using method equal share. Oh, sorry, all of them are using a variation of method equal share, but 50% of the budget was dedicated to deliberation, and 50% of the budget is dedicated to individual votes. So what I name is the method equal share for hybrid votes. So it combines the deliberation groups and individual voting. Sorry, I may not have enough time, but I can go into more details later. But so what happened? So 50% of budget is used for individual voting, and 50% of budget, they form committee criteria groups. So citizens are formed into different criteria groups. It could be like, for example, they assess projects based on this particular criteria. And so 10%, for example, 10% of budget is for new and interesting projects. And these are the criteria that citizens came up with themselves. They have 8 criteria to go through, and they assign points according to these criteria. And this is the platform they interacted with, and they can see how much budget actually comes from the group discussion and how much budget actually comes from the individual budget. And eventually,
Josh, I think we've run out of time. So I suggest that you can go into more details in the breakout room.
Yes, I can do that.
Okay, great. Thank you very much for the talk. And our next talk is by Soroush Ebadian about achieving the optimal distortion with few queries.
Okay, do you have my screen?
Yes, yes.
Awesome. Thank you, Dominic, and thank you everyone for staying. This is the last talk, I'll be quick. Okay, so as Dominic said, this is about distortion and queries. And Aris Philos Ratsikas has a nice COMSOC presentation back in 2021 on this topic, and this is a follow-up work on that line of work. And this was presented at AAA. We were fortunate to win an award. And so let me briefly discuss what does distortion mean, and what do we do with queries in this framework. So the paper is about single winner voting and one-sided matching, but I'm going to stick with one-sided matching. We have n agents, n items. We want to match it in a way that is efficient, maximizes social welfare as as a main objective. And this implicit utilitarian framework, due to Prakash and Rosenstein from 2006, is the following. Suppose these agents have internal utilities for the items, like the boy likes the starry nights at like number 50. We have these cardinal values. If we have access to these cardinal values, we can maximize cardinal objectives like maximizing utilitarian welfare, call it the efficient matching. But instead, because it's difficult to elicit, we usually work with rank preferences because it's easier to elicit, and we use ordinal mechanisms. But when we only look at these these rank preferences and make decision based on that, suppose that we match in this way, then we're going to lose some efficiency. We're going to lose on this cardinal objective because of incomplete information. And this ratio, this 120, for instance, divided by 150 is called, the inverse of it is called the distortion. And we want to get the best approximation to this cardinal objective, this maximum utilitarian welfare as possible. Okay, so this is distortion. And if you do not have any assumptions on the utilities, you cannot do much better than like root n with deterministic rules. You cannot better than ON, order of n. N is the number of both agents and items. And this line of work started from Amanatidis, Berpas, Philostratsikas, and Voudouris. They asked, what if we could sit with the voters, with the agents, and ask a few additional value queries, like how much you really like this item. And the main theorem of the paper is that if you have lambda, like let's say 2 queries or 3 queries, you can get n to the order of n to the 1 over lambda. And we also have the similar result for single winner voting, showing that you can get order of like lambda times minimum of n and m. N is here is the number of agents, m is the number of voters. Sorry, my bad. N is the number of agents, m is the number of candidates. And you can do this in polytime. I'll quickly go over prior work and how we fit into this picture. So as I said, Amanatidis et al. Started this line of work. They showed some lower bounds, and a recent work by, again, the same set of authors, they showed an upper bound of 2 times root n. So if you can ask 2 queries without any assumptions on the utilities, you can get a distortion of root n. We could improve this for lambda queries. So if you have lambda, for a constant lambda, you can get roughly n to the 1 over lambda, which is roughly tight. There's this gap of lambda squared, which if lambda is constant, technically it's tight up to constants. But the main problem, I think, in my view, the main open question is what happens when lambda is less than log n, but a super constant. So for one-sided matching, is order of log n many queries enough for constant distortion? Can we approximate this objective well enough with only log n queries and with log m number of candidates for single winner voting? There are some lower bounds by Amanatidis et al. Again, and Kargianis and First recent work. Yeah, that's it. Thank you.
Thank you very much.